Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic is path independence and conservative vector fields. All right, some definitions are in order here. So we have a vector field F. So let F be a vector field defined on an open region D in space, and suppose that for any points A and B in D, so in other words, these are x, y, z points, A, B, and D, the integral from A to B of f dot dr is the same regardless of the path taken from A to B, right? So we saw that this was not the case last time, that we could take different paths, or as it was two lectures ago, we take different paths from the end of the same point and began at the same point and get different line integral values. But if this is the same, regardless of the path taken from A to B, then we say that the integral f dot dr, that line integral, is what's called path independent in the region D, and that the field F is a conservative vector field on D, right? So the integral is path independent, if this is the case, and the field itself is called conservative. And we know from examples that not every vector field is conservative, right? The ones we had in the previous examples, most of them, I think all of them, were not conservative. Okay? So that's the definition. Now some facts of how this can help us. So fact, a field F is conservative if and only if F is the gradient field. F is the gradient field for some scalar function f, right? So fields are conservative if and only if they are the gradient field for some function f, okay? So that is to say, f equals grad f, or del f, for some scalar function f, right? So if this is true, then capital F is conservative, okay? And if this is the case, f is called the potential function. F is called the potential function for capital F. Okay. So, for example, electric potential is going to be some scalar function, right? And its vector field is an electric field, right? So, or I'm sorry, its gradient field is an electric field. So F is the potential function for electricity. The field, the gradient field, capital F, is the electric field, okay? And so what do we have here? Well, if we think of, so remember that grad F is just the partial derivatives with respect to each of the variables in F. So partial F, partial X, partial F, partial Y, partial F, partial Z. So if we think of grad F as a derivative, in some sense, for the function f of x, y, z, right? Then what we get a version of the fundamental theorem of calculus, actually, which involving line integrals and conservative fields. And it says the following. So if we think of grad f as being this derivative for this function, right, we get the following theorem. Let me put it up here because it's long. And before we saw that fundamental theorem of calculus gave us that crucial relationship between integrals and derivatives. Well, now we're going to have what's called the fundamental theorem of line integrals, and it will give us a relationship between line integrals and gradient. Okay? And it says the following. So f is a conservative vector field. Right? That is to say that f is equal to grad f for some scalar function, little f, right? And the components of capital F, the components are continuous on an open, connected region D in space, and we'll get to the definition of those terms shortly. In general, though, I mean, things we work on often satisfy these hypotheses without any difficulty. Then, for all A and B in D, regardless of the path connecting, so the path, let me actually put over here, the path being some R of t, right, some curve connecting A to B, we have the following powerful result, that the integral from A to B of f dot dr is equal to, well, we know that capital F is grad f for some little function f, some scalar function f, and this is just f of b minus f of a. Note the immediate similarity between this and fundamental theorem of calculus, and the idea being that now we're thinking about grad f as being some derivative, right? Basically, we have a derivative and then some dr term. We're looking at just the function f of b minus f of a as being the function that comes out of grad f. Okay? So let's go ahead and use this theorem. Okay, so let's show that capital F equals yzi plus xzj plus xyk is a conservative vector field, and then compute the work done moving a particle along any smooth curve C connecting the points -1, 3, 9 and 1, 6, -4. Okay, so two parts of this problem. First thing is first, we're showing that this particular field is conservative, and then if we've done that, well, we can then use the fundamental theorem of line integrals to show what the work is on any path connecting these points without a whole lot of difficulty. Okay? Okay, so to show it's conservative, we must find a function f so that capital F equals del f, all right? And we know that del f is partial f partial xi plus partial f partial yj plus partial f partial zk, right? And our capital F is yzi plus xz, oops, plus xzk, xzj, excuse me, xzj plus xyk. Okay? So we want a function such that partial f partial x is this, partial f partial y is this, and partial f partial z is that. Well, lucky for us, this one is extremely easy. So if we were to integrate this with respect to x, that would be like saying what function has partial derivative with respect to x equal to yz. Well, it turns out that's exactly the same integral we get if we integrate xz with respect to y, and it's the same integral we get if we integrate xy with respect to z, right? So in other words, we're going down the line and get the same result every single time, and it turns out the function here is xyz, right? The function xyz has exactly, so if this is our function xyz, it has exactly this gradient, right? This gradient field. So yz, xz, xy out of this function right here. So we'll see down the road that it won't always be this easy. It won't always be this easy. Okay? So there's a function that works. Therefore, f is equal to the gradient field of that function. Therefore, f is conservative. Okay? F is conservative. Okay, well, as a consequence of being conservative, f has the path independence property. Okay, so if I want to get the work out of this thing, let me do it down here. I want to get the work in moving this particle. Well, again, it doesn't matter what smooth curve we choose, right? It does not make a difference. So work is the smooth curve, integral of the smooth curve f dot dr. Well, for us, all we care about is that we know this is conservative, so all that matters to us is the endpoints. It doesn't matter what method we took to get there, right? All that matters is the endpoints. So the endpoints for us, negative 139, 16, negative 4 of grad f times dr, right? And we know from the fundamental theorem of line integrals that all that matters here now is, well, we know the f that is actually happening here. This is the f, so we plug in these points of that f and subtract, right? So this is just f of 16, negative 4 minus f of negative 139. Let's see, a plug in, so 1 times 6 times negative 4 is negative 24. Negative 1 times 3 times 9 is negative 27, so it's plus a positive 27, so it's equal to 3. So there's the work. And that was a whole heck of a lot easier than what we did before in the previous section, because we were able to use that theorem to help us out here, knowing f was conservative. So the bottom line is that it clearly is preferable to work in conservative fields. It makes life a lot easier in computing these line integrals. That's for sure. Okay, so a few facts here are in order. I mentioned earlier that certain assumptions were required of our fields, things like open and connected regions. Let's cover those briefly. For all the work we'll do in this course, we'll have no problem, but in the future, when you look at things in more general settings, all of a sudden there could be issues coming up if you're not careful. So some assumptions at work here. Okay. The first thing is the curve. So I said that any path between the 2 points will work. Well, I mean, essentially that's true, but the curve C needs to be piecewise smooth. And what that means is that you can have sharp corners. Right? I have no problem with sharp corners, so you can have a bunch of line segments zigzagging along between the points. That's no problem. But you can't have gaps. So you can't be walking along a curve and all of a sudden have a big gap and then have another curve start up. It has to be smooth piecewise at least. So sharp corners are okay. Sharp corners okay here. But no gaps. Okay, so that's not a big deal. And D is open, so D is an open region. That means it doesn't contain its boundary. Doesn't contain its boundary. Okay, so like the interior of a circle works, but a circle itself doesn't work because the circle contains its boundary. So it's kind of a fine point, but we'll see it's not a big deal for us usually. And it also has to be connected. So in other words, the region D that your field is defined upon, the domain set of your field, has to be open and connected. And connected just means it's all in one piece, right? And so what's nice is that most vector fields, they have domain r squared, or I'm sorry, R2, not r squared, R2 or R3. In other words, most vector fields have domain the entire plane or all of space, right? And in both cases, they're both open and connected. So, and these are both open and connected, right? It takes sort of a funky field, not a funky field, but a field defined on a funky subset to sort of violate this. So these are usually no problem at all to have these two requirements satisfied. Okay, so that's some behind the scenes kind of stuff going on. At least you're aware of it. Okay, so fact. This is a useful thing too, especially when you move into things like complex analysis. This comes up all the time. So if F is a conservative field on a domain D, then the following is true. Then the line integral over a curve C equals 0 around every closed loop C in D, right? So the integral the line integral of f over c is 0 as long as c is a closed loop. So if you think back to the last section, we had an example of a field where we integrated around a circle, around a full circle. We called it circulation, and we got a non-zero value. We got 2 pi. Well, clearly that means right away that that field we integrated over was not conservative. Okay? So to summarize, when you have a conservative field, you have nice things happening. They have path independence. That's nice. Right? They have path independence. And the closed loop property holds integral around a closed loop. Remember, this notation here meant it was a closed curve, C, closed loop, equals to 0. Okay? So they have nice properties. So the next logical question to ask is, well, how do we determine this? In other words, before it was easy. We had a very simple field, a very obvious function f presented itself to us. Well, not always the case, unfortunately. So how do we determine if a field f is conservative? Okay. So let's see. We'll answer that question next. So we ask ourselves, how do we determine is a field conservative or not? Okay, so question gone. Here comes the answer, at least in some form. So fact. So we have, I'm going to work first in the 2D case, and then we'll move to the 3D case. So you have some vector field, pi plus qj, and So it's a vector field. And let's see here. What are the requirements? So P and Q, well, they have to have continuous first order partials, and we'll see why in a minute. And let's see here. You want to have what's called an open. This time I'm going to use even a stronger condition. I'm going to call it a simply connected region D in the plane. Okay, so you have this vector field. P and Q have continuous first order partials on an open, simply connected region D in the plane. And the following requirement satisfied. So partial P partial Y is equal to partial Q partial X everywhere in D. Right? So that's the big one there, right? That these two, that this equality is always satisfied at every point in D, then F is conservative. Right? So as long as you satisfy this other rigmarole up here and you get this to happen for every point in D, you're in good shape. And also, I guess it's worth noting too, so note simply connected is a stronger version of connected. A simply connected region is one without any interior holes, essentially. So, for example, I don't know. There's a region with a hole in the middle of it. This is not simply connected. Neither's that. So, I mean, as long as you don't have any holes in your region, and I mean, it's pretty rare that we're sort of playing with sort of odd things like this anyway. So mostly we deal with regions that are pretty nice, but these are not simply connected, so this theorem fails to hold on those kind of regions. So just sort of be aware of that in the back of your mind. Okay, so let's try this out here. Get rid of the fact. We'll try a couple problems here. So example, determine whether the vector field F equal, or F of xy equals x minus y I plus x minus 2j is conservative. Okay? Well, our scalar functions, so our x function is x minus y, or I'm sorry, I function, p of xy, q of xy, q of xy is x minus 2. Okay? Everything is satisfied here. Derivatives have no problem with continuity. This is defined on all the planes, so it's open, it's simply connected, there's no issue with that. So our only question is, let's look at partial p partial y. Well, it's -1. Partial q partial x, +1. Well, they don't sync up for any point in the plane, so these are not equal. F is not conservative. All right, so they don't sync up for any point in the plane. Done. Okay? So that was one that didn't work. That was easy enough. Let's see if we get one that does work. So let's leave the question up here, but change the vector field. All right. So let's now check and see whether or not this field is conservative. So how about 3 plus 2xy is the I piece, and x squared minus 3y squared is the j piece. Okay? Let's check this out here. So again, everything is fine, open, simply connected, no issues, continuity is no problem. So p of xy is 3 plus 2xy. Q of xy is x squared minus 3y squared. Okay. So now we're going to check partial p partial y. that gives me 2x. And partial q partial x also gives me 2x, right? And so, in fact, these are equal for every point in the plane, right? So any point in the plane that you give me, the partials will be equal at that point, right? Okay? So, as a consequence, f is not continuous, f is conservative. F is conservative, right? Because it does satisfy the requirement properties, particularly this property, throughout the domain of R2. Okay? So, it's a conservative field. What does that mean to us? It means that it's the gradient field of some scalar function f. And in particular, well, it's nice and it's conservative, but in order to use the fundamental theorem of line integrals, you're going to have to find out what that potential function is. So, in order to use that theorem, let me actually get rid of everything but the field itself. You need to figure out what is this field's apostrophe s potential function. Because otherwise, we can't use the fundamental theorem of line integrals. We can't do it. Okay, so let's see here. We want an f such that there, f equals del f. And this time, well, it's not going to be quite so obvious. We have to do a little bit of work here. So we want partial f partial x to be 3 plus 2xy, and we want partial f partial y to be x squared minus 3y squared. And these must be satisfied simultaneously by the same function, right? So we're going to use, in some sense, what is referred to as partial integration on these functions to see how they behave. So we'll start off by integrating both sides of this equation with respect to x. So if we do that, integrate partial f partial x dx, and we integrate 3 plus 2xy with respect to x. Well, these are going to cancel out and give us back the old function again. So we'll have f of x y back, right? So we integrate with respect to x the partial derivative with respect to x, and we get back the original function again. This is f of x y. And this over here is going to be what? 3x plus x squared y. And then there could also be a function over here exclusively of y. So think back to integration of a single variable. When we integrated, there could always have been a constant term on the end, right? Because constant terms, when you take the derivative, they become 0. Well, the same idea applies here. This function is entirely in terms of y. So if we took the derivative of it with respect to x, it would be 0. It would go away. So it wouldn't show up here. So this thing at the end could be 0, or it could be something else in terms of y itself, right? But it's a constant with respect to x. That's why it would go away when you took the partial with respect to x, okay? All right, so now that's our f of x, y. So the question is, what is g of y? Well, let's differentiate both sides of this equation with respect to y, right? So we're going to take partial f partial y of both sides here, partial f partial y of both sides. And then, well, over here, actually, we just take partial y of both sides. Don't need the f there, really. But on the one side, on the left side, we get partial f partial y, right? If we differentiate f of x, y with respect to y only, it's partial f partial y, okay? On the right side, well, this term goes away. The 3x is gone. And the x squared y leaves us just an x squared. And the derivative of gy with respect to y is g prime of y, right? And that's all it is. I mean, there's only one variable to be differentiated with respect here. right? It's just a function of y. So this is g prime of y. So here's one expression for partial f partial y. But another expression that also has to be satisfied is this one up here, right? This is part of our requirements to be a potential function, right? It has to be this, but it has to be this by analysis. So this must be equal to this thing, right? So we have x squared minus 3y squared equals x squared plus g prime of y, okay? Because these are both equal to partial f partial y. All right, so what does that mean? Well, it means that g prime of y is equal to negative 3y squared. Okay, well, we're almost there. Remember, our goal is, what is f of xy? Well, before I took partial y of both sides, right, we don't need that, right, I had it here. It was f of xy equals this thing plus a function of y. Well, we're almost to that function. We know what g prime is. Let's integrate both sides. Integrate g prime of y with respect to y, integrate negative 3y squared with respect to y. What comes out of this by FTC is g of y, right? What comes out of the other side is negative y cubed plus a constant, right? So k is a constant, right? So this is the function gy. So to summarize here, what do we do to do this? We had these equations that had to be satisfied simultaneously. So we integrated to get an expression, f of xy, with a function gy in there. Then we differentiate with respect to y to get this thing into a partial f partial y form. Set them equal, integrated again to go from g prime back to g, and now we have g. So what's our potential function? Well, it's f of xy equals 3x plus x squared y, not plus, but minus y cubed plus k, a constant, right? There's a potential function, and in fact, we see that just like a function has infinitely many antiderivatives based upon the constant there, right? This vector field really has infinitely many potential functions. Infinitely many potential functions. You could just put in any old constant that you darn well felt like. Okay? So, to back up here a minute, we confirmed this was conservative. Okay? So it had a function that was potential to it. We found the potential function. Now we have a conservative field, a potential function. We can use fundamental theorem of line integrals to evaluate integrals in that field. So let's do that. So I don't want to erase my potential function, and I don't want to erase my field. Everything else can go. Okay. So now, let's do one more thing here. Let's evaluate integral over a curve, FDR, where C is the curve given by, R of t is e to the t sine ti plus e to the t cosine tj. And let's put t between 0 and pi, and we'll use the same old f that we've been using. Okay. All right. So this is almost easy street, but there's a little snag, I guess. So we want to use the fundamental theorem of line integrals on this problem. So we know that this is equal to 0 to pi, and that's grad f dot dr. The one problem that we have to deal with is, well, r is in terms of t, and f is in terms of x and y, right? So f is in x and y terms, r is in t terms. Okay? So what do? Well, I'm having t range between 0 and pi, so let's just get xy points along this plane curve here, right? So in other words, when I plug in 0 to r, I get e to the 0 is 1, sine of 0 is 0. So I get 0, and e to the 0 is 1, and cosine of 0 is 1, so this is just 1. So along this plane curve, r of t, when I plug in t equals 0, this is the point I sit at. Okay? And when I plug in pi, e to the pi times sine pi is still 0. E to the pi times 1 is e to the pi. So here are the xy points, which are the limits of integration for the integral up here. Okay? So these are the xy points we get from RT when we plug in these limiting t values. So where are we here? Also, it's worth noting too, well, let me show you first what the integral looks like. So integrals of f dr, right? Let's see. So now our points are 0, 1 to 0, e pi grad f dot dr. All right. Okay. And so we need to, so now this becomes f of 0 e to the pi minus f of 0, 1. Excuse me. So the only thing is there's this k over here. So I mean, that's a potential function for any constant. So we can plug in any old k we want to here. Make it 0. Make life easy on ourselves. So we may as well make k 0 and call it that. So when I plug this in, I plug in 0 and e to the pi. So that's zeroed out. That's zeroed out. So we have minus e to the pi cubed. And then we have minus, so that's zeroed out, that's zeroed out. We have a minus negative 1, so that's negative e to the 3 pi plus 1 is what we should have here. And for some reason here, I've got two negatives. Why is that? So I plugged in e to the pi. I have minus e to the pi here. Why do I have minus e to the pi? Did I make a mistake up here? When I plug in pi here, I get e to the pi. Oh, yeah, cosine pi is negative 1, so this should be minus e to the pi. Yeah, excuse me. That should be minus e to the pi. That's minus e to the pi. Minus e to the pi, and that should be plus. So yeah, that was my mistake there, yeah. But this should be e to the pi plus 1 is this line integral, right? So really, I mean, we went through the whole problem in some sense from beginning to end. We found the conservative vector field. We found the potential function, and we used that potential function to evaluate the line integral using the fundamental theorem of line integrals. Okay, so that was all the 2D case. The 3D case is more or less the same way. So I'll show that here, and we'll do an example. But it's basically the same idea. There's not a whole lot more to it, but we'll do one anyway. And the theorem, the criteria is almost the same except for an extra term or two. So here's a fact. So we have this 3D field, and it's pi plus qj plus rk. And that's a vector field. And all of these guys, P, Q, and R, have continuous first order partials on an open, simply connected region D. And this time we're in space. We're not in the plane, so we're in space. And then the following relationship holds, or the following relationships hold. Partial P, partial Y is partial Q, partial X. partial p partial y is equal to partial, where am I here? Partial r partial x. Let me see, am I looking at this right here? No, it doesn't look right. Wait, hold on. So partial p partial y. So you're switching p and q, and you're switching x and y. And you want to switch p. So this should be a partial z. Yeah, it should be partial z there. That looks better. And then partial q partial z equals partial r partial y. So yeah, so you're flipping. So p and q and x and y are flipping, and then p and r and x and z are flipping, and q and r and x or y and z are flipping. So all of those hold throughout D, then F is conservative. So this time you've got not only one criterion to check out, you've got to check out 3 and make sure they all apply for a conservative field. Okay, so let's do an example here. So the facts are up here. Let's again take a field and is it conservative or not? And if so, can we find the potential function? So the field will be e to the x cosine y plus yzi, and xz minus e to the x sine y j, and xy plus zk. That's our field. And let's test is that conservative, and if so, let's find the potential function. So is f conservative? If so, what is the potential function? Little f. Okay, so we have our 3 pieces. Pxyz is e to the x cos y plus yz. Q of xyz is equal to xz minus e to the x sine y, and r of xyz is equal to xy plus z. Okay, so let's do our test here. So let's see here. Partial r, partial x. We'll start there. That gives you y. So that needs to be equal to partial p, partial z. So that's true. Yeah, it works. Okay. And let's see, what else? So what have I got next? Partial p, partial z. I already had that one, didn't I? Okay, I see what I'm doing. Okay, yeah. So partial r, partial y is equal to x. So that must be equal to partial q, partial z. So that works. So that's partial q, partial z. And then how about partial p, partial y? That's the only one that we got to worry about a little bit. So partial p, partial y is negative sine y e to the x plus z, right? And that's got to be equal to partial q, partial x. So partial q, partial x is z. Let's see here. So negative cosine is the derivative there. So that's minus. It's minus cosine. Did I write this down right? So that's minus cosine. Let's see, did I make a mistake here? Or am I just looking at this thing correctly? So let's see. So partial p, partial y looks good to me, yeah. How about partial q, partial x? So So we have z, and then let's see, the derivative here, oh, partial x. Okay, yeah, partial x, that looks better. So e to the x sine y, there we go. Yeah, all right. So everything checks out there. So these relationships all hold correctly, therefore f is conservative. F is conservative, all right? Now, and also, you know, the domains of all these guys are R3, so everything's continuous and open, simply connected and whatnot, so that's good to go. So we need to find the potential function. We need to find the potential function here. So we need f so that delta f is equal to capital F there. So we got to have partial f partial x equal to e to the x cosine y plus yz. Got to have partial f partial y equal to xz minus e to the x sine y. And got to have partial f partial z equal to xy plus z. So all three of these must now be concurrently satisfied. So we have an extra requirement here than we had from the 2D case. Okay, so but we'll start the same way if we integrate both sides of this equality with respect to x. Then on the left-hand side we'll get out a function of three variables, and on the right-hand side we'll get out integral e to the x cosine y plus yz dx, which is just what? Let's see here. So we know with respect to x, so that is x. Wait, what am I doing here? Am I not viewing this correctly here? That's right. Yeah. So let's see. X. So this is e to the x cosine y. Yeah, that's right. Yeah. Because y is a constant. I'm not thinking straight. So, and then over here, this is plus xyz, right? And then on the end, we have this function g of, am I using g or h? Yeah, I'm using g. We have this function g of yz, because if it's a function only of y and z, again, it'll act like a constant with respect to x. So this could be a constant number, could be a function of y and z. We don't know what it is at this point, though. But that's our f of x, y, z. So now, let's go ahead and differentiate both sides of this new equation. So this is f of x, y, z with respect to y, and then we'll get an expression in terms of y, and then we'll kind of play from there. So on the left-hand side, we have partial f, partial y. On the right-hand side, we have negative e to the x sine y plus xz. And then over here, we have what? We have a partial g, partial y, right? Is that what I have here? Is that what I want? Yeah, it looks good, yeah. So, yeah, so you have this partial g, partial y over here. But now, remember that this expression has to match this expression, right? Because they're both equal to partial f, partial y. So what we have is we have negative e to the x sine y plus xz plus partial g partial y equals to xz minus e to the x sine y. So what does this imply? Then it implies that partial g partial y is 0, right? Which means that this function, right, with respect to y was a constant, which then implies that there's not a y term in here, right? If there was a y term in here, anything at all, this would not be 0. So, in reality, g of yz is really just some function of z alone, right? It's just some function of z alone, right? So again, this derivative being 0 implied that there's no y term in here, right? There's no y term in here. There's only z terms. Okay? So let me erase some of this stuff. Let's see. We can probably get rid of that, and probably get rid of that. And so now what we have is we have f of xyz equal to e to the x cosine y plus xyz plus some h of z. So now let's do one more derivative. Let's take a derivative with respect to z of both sides. So we have partial f partial z on the one side. The other side we have xy plus h prime of z. Okay? But, you know, this thing has to match what's already up here in terms of partial f partial z. So this has to match that. So therefore, xy plus h prime of z better equal xy plus z. Well, that means that h prime of z is z. Integrate both sides with respect to z. Right? That means h of z is 1/2 z squared plus k. K a constant. Right? That's h of z. And so, at the end of all of this, your potential function is a function of three variables. E to the x, that's a y, cosine y plus xyz plus 1/2 z squared plus k. Right? And again, there are infinitely many potential functions for this vector field based upon choices of k. So the same idea. We just kept integrating and differentiating until we got down to what we had to have at the end, which was just a definition of a function of z there. Okay, so that concludes the section on independence of path and conservative fields.